Hello everyone. Today I will introduce an efficient and affordable setup to capture HOM interference with the CISS camera. If two photons arrive at the beam splitter at the exact same time and from the same direction, something called interference occurs. Instead of going in different directions, they buddy up and leave the splitter together in the same direction. It's like they merge in one photon. After the photons go through the beam splitter in the HOM effect, they essentially have two possible outcomes. They can either both exit from one side of the beam splitter or one exits from each side. Now, if we look at each of these outcomes, they are equally likely. It's like flipping a fair coin. You have two possible outcomes, heads or tails, and each outcome has an equal chance of happening. So the probability for both photons existing from the same side, transmission, and the probability of one photon existing from each side, reflection, are both 1 out of 2, or 50%. Let's go back to our experiment, check out the principle and methodology. This experiment uses a special crystal that reacts to laser pulses to create pairs of identical photons. By using various optical components, like a polarizing beam splitter, wave plates, and optical delay line, the experiment controlled the polarization angle and adjustable coherence lengths of these paired photons. Then, by employing single-mode fibers, quarter wave plates, and half wave plates, it maintains the polarization of these photon pairs. Finally, the experiment utilizes the crystal birefringent properties to separate these photon pairs spatially, confirming their HOM interference characteristics. To verify the likelihood of single-photon events in the HOM interference setup, the experiment used photons with a wavelength of 790 nanometers. The camera-captured parameters are listed in this table. Random continuous sampling of 40,000 frames showed a single-photon probability of 0.0002, which closely matched the expected theoretical calculation. This graph shows the total sum of pixels counts for each frame number in the sequence. A comparison of the raw data of single-photon events with different intensified cameras was conducted to evaluate their signal-to-noise ratio. The intensified camera from CISS captured the original image with only a single photon. The grayscale values were linearly mapped according to the minimum and the maximum values for automatic contrast enhancement. Picture number 5 displays a single photon image captured by an intensified camera from another camera manufacturer. It can be concluded that the noise level of the CISS intensified camera is almost zero. So in conclusion, the CISS intensified camera features an optical shutter with an impressive minimum of 3 nanoseconds combined with an exceptionally sensitive image intensifier. Through experimental validation, it has been demonstrated that the CISS camera exhibits performances comparable to or even superior to well-known brands. Consequently, it emerges as a smart and affordable choice for researchers engaged in experiments such as the capture of quantum entanglement and the verification of quantum interference. For more details and information, please reach out to me. Thank you for your attention.